designed for human immunodeficiency virus that attack the body immune system. If HIV is not treated, it can lead to AIDS, acquired immunodeficiency syndrome. HIV genome has two identical single-stranded DNA known as ssDNA and consists three main structural genes, which are ENV genes, GAG genes, and POL genes. Moreover, HIV also known as proviral DNA, which in active viral form that has been integrated into genes of host cell. For instance, when HIV enters a host CD4 cell, HIV RNA will change to HIV DNA. Then the HIV provirus gets inserted into the DNA of CD4 cell. When CD4 cell replicate, the HIV provirus also replicate and pass from one cell to the next. So, how are we going to stop or inactivate this integrated HIV DNA? One of the most promising gene editing tools is by using CRISPR-Cas9. CRISPR-Cas9 is an acronym for clustered regularly interspecies short palindromic repeats of gene informations where it consists two key molecules, Cas9 enzyme and guide RNA. This advanced technology is designed to inactivate or remove the integrated provirus DNA of HIV from host genome. Therefore, the applications of CRISPR-Cas9 editing to target an inactive integrated viral genome such as HIV has shown positive results in several in vitro and preclinical studies. So, CRISPR-Cas9 represents a likely strategy against HIV infections and achieving HIV.
Next, the CRISPR-Cas9 system is a natural mechanism in prokaryote that functions as an adaptive immune system against invading genetic elements such as virus. As mentioned in introduction, the system consists of CRISPR and CRISPR-associated protein, Cas. When a virus infects a bacteria, the bacteria integrates a small piece of virus DNA into its own CRISPR array, creating a new specimen. The CRISPR array is transcribed into pre-cRNA that form effector complex with Cas protein. If the effector complex encounter a viral DNA sequence complementary, the CRISPR-Cas9 system can be adapted for HIV therapy by fusing the cRNA and trans-activating CRISPR RNA into a single guided RNA known as the sgRNA. This sgRNA, along with the Cas9 protein, can be introduced into a cell to cleave DNA at the LTR sequence to inactivate the HIV-1 virus. The cell DNA repair mechanism can fix the cut made by the CRISPR-Cas9 system using non-homologous end joining and HIEG or homology-directed repair (HDR) and HEG can introduce change in the repair DNA while HDR maintains its size uniformity. Surprisingly, the DNA repair process known as non-homologous end joining and HEG can also effectively repair the non-integrated HIV-1 provirus. This discovery highlights the potential of CRISPR-Cas9 in treating HIV or AIDS by targeting the virus and its proviral DNA in latent cells. In addition, for targeting HIV-1 genome, CRISPR-Cas9 technology can also be used to block HIV-E3 by editing of co-receptor. HIV enters host cell through binding to the CD4 receptor and CCR5. As CD4 is critical for function immune system, disruption of CD4 is an advisable strategy in preventing HIV infection. In 2015, Lee et al. Used adenovirus deliver CRISPR-Cas9 combined with sgRNA, targeting the fourth exon of CCR5 to disrupt CCR5 expression, which is a huge discovery in HIV therapy.
The next method is reactivation of latent HIV. It is important to reactivate dormant virus in host cells, induce cell death by HAART and activate antiviral immune response in order to eliminate latent HIV reservoir. This strategy is known as shot and kill. This mechanism is effective in increasing HIV transcription, protein expression, and variant production. This technique also combined with latency reversing agents to reactivate latent HIV within CD4 cells. It will allow ART and the body's immune system to attack the virus. The important to combine with latent reversing agents because it will help patients using HAART cope with a number of side effects and improve the effectiveness of removing the HIV-1 latent reservoir. Latency reversing agents such as histone deacetylase inhibitor is used to reactivate viral gene expression. However, this strategy might not be able to target all viral reservoir, making it less effective. Therefore, CRISPR-Cas9 technology might be useful for reactivating dormant HIV-1 viral reservoir. To activate or repress gene transcription, many researchers have paired defective Cas9, d-Cas9, fusion protein with sgRNA specific to effector domain of the target DNA sequence. The catalytically inactive d-Cas9 coupled with transcription activated domains in HIV-1 latent reservoir can increase viral gene expression, thereby enhancing the shock and kill strategy. Now, we can see that the CRISPR-Cas9 mediated stimulation of viral transcription has been offered a different strategy to target and activate viral gene expression in dormant HIV reservoir. The next method is reactivation of host restriction factors during HIV-1 infection. Scientists found that the CRISPR-Cas9 helps in induce the expression of the restriction factors A3G and A3B in human cells. The A3 restriction factors of HIV can induce a mutagenesis of proviral DNA and inhibit the retroviral replication. The activation of the expression of restriction factors can be one of the alternative strategies to prevent HIV-1 replication. However, studies on the application of CRISPR-Cas9 technology in activating cellular host factors to inhibit HIV-1 infection are very limited. Thus, scientists discovered the restriction factors such as serine incorporator 5, serine C5, human silencing hub, HUSH, and NONO may be the new target to be considered for this application. These restriction factors can inhibit HIV infection through different mechanisms. We can see this technology may provide new strategies to treat HIV-1 infection, but still need more effort to further develop this toolset.
Hi, my name is Nur Emira Natasha. So next, we proceed to the limitation of CRISPR-Cas9. The first one is off-target effect. CRISPR-Cas9 has the potential to introduce unintended mutation at the site that is similar to the target DNA sequence. This off-target occurs when Cas9 acts on untargeted genomic sites and create cleavage that may lead to unintended changes in genome, which may have unforeseen consequences. Researchers are continually working on improving the specificity of CRISPR-Cas9 to minimize off-target effect. The second limitation of CRISPR-Cas9 is delivery challenge. The efficiency of delivery of the CRISPR-Cas9 system to the target cells or tissue remains as a challenge. While it works well in certain cell types, delivering the system to the specific tissue organs or the whole organisms can be difficult. The researchers are exploring the different methods such as viral vectors, nanoparticles, and other techniques to improve the efficiency and specificity of delivery.
In conclusion, CRISPR-Cas9 is more convenient and have efficient design of the target site. It can be used not only in HIV/AIDS therapy but all in every research field. We just need to change the RNA for different target DNA to find the most effective site. The CRISPR-Cas9 system is a good gene editing tool applied in a gene therapy field. However, the high target efficiency and effective delivery are essential for successful application in clinical trial. It is important and put in consideration to design and screen effective RNA to reduce the off-target effects and the safety and delivery efficiency of the CRISPR-Cas9. However, they may be exciting and promising advancement in the field of the HIV/AIDS if the CRISPR-Cas9 technology is combined with the other strategy to help to overcome this limitation.